Hello everyone, my name is Hunter and this is my first hot wash video, and I basically want to do an overview of where metabolic processes are happening and what processes happen based on our different states of being. So we're going to focus just on heterotrophic metabolism, and that's gaining energy by consuming matter and converting it into usable energy or molecules. We're not focusing on autotrophs or chemotrophs that gain their energy other ways. So an overview of metabolic processes can be kind of complex. We're going to simplify it quite a bit because if we look at this big map, there's a lot of things going on, and they're all interconnected based off the intermediates. How much we have of them is going to push them into different areas so that we're being energy efficient. So the general pathways that we're going to talk about first is glycolysis. So when glucose is broken down into pyruvate and then thrown into the citric acid cycle so that we can have energy in the form of NADH, NATP, and FADH2. If we have not enough glucose, then we're going to build it up, and that's gluconeogenesis. And we can put smaller molecules together like amino acids, pyruvate, or other non-carbohydrates to build up glucose and then use it as we need it. If we have too much glucose, we'll go on to the next one. That's called glycogenesis. Glucose can be linked together and stored as a molecule called glycogen. You can see in the picture there that glycogen forms in strands with a bunch of branches. That's done on purpose so that we can access as much glucose as we need at whatever rate we need, because you have to break those down from the ends of the branches inward. So if you have lots of branches, you can access it really quickly. And that breakdown of glycogen back into glucose from the branch pieces is called glycogenolysis or glycogenolysis, and that's our next one. And then we're not going to talk about it a lot, but the pentose phosphate pathway allows us to change 6 carbon sugars into 5 carbon sugars and create different sources of information or energy like nucleic acids. So big cycles we're going to talk about are the citric acid cycle and the urea cycle. The citric acid cycle is where we get most of our energy, like I mentioned before. A big contributor to that is pyruvate, which gets converted to acetyl-CoA and then put into the citric acid cycle so that we can get energy. And then the urea cycle is mainly to get rid of excess nitrogen, whatever we consume or whatever we don't need from amino acids in excess. Those nitrogens can be pulled out, put into the urea cycle, and then excreted, because if we have too much, they can be toxic. And then beta oxidation provides energy by creating acetyl-CoA from breaking down long fatty acid chains, which is just another form of food that we eat. And so those can go into acetyl-CoA or succinyl-CoA, put in the citric acid cycle, and we can get useful energy out of it. So all metabolism is happening all the time throughout our whole body, but the main components that do that, or our main organs, are number one, the liver, which is a wide variety of metabolic processes, adipose tissue or fat, which is a form of energy storage, which is important because it insulates us and gives us a reserve of energy if we need it. Kidneys that convert amino acids that have those amino groups on them, the nitrogens. They can take those nitrogens off and put them into the urea cycle and then create things like glucose so that we can have energy from that. Our muscle mostly uses energy. It keeps us alive so that our heart can beat and that we can breathe with our diaphragm. And then our skeletal muscle moves us around and generates heat. And that's really how most of our processes happen, is through muscle contraction. And then our brain that controls everything uses a very large amount of energy in the form of glucose so that it can fire off its action potentials and keep us running. So we're going to next look at how our energy use changes and our metabolic processes change based on the activity levels that we have. So soon after we eat, we're going to use the glucose we need to have our energy, and then any excess glucose is first going to be put into glycogenesis, and we're going to build up our glycogen stores, but we have a limited amount of space for that. So once our glycogen stores are filled, it's going to convert whatever glucose is left into triacylglycerols. Those are going to be put into adipose tissue, which does the same thing with excess glucose. If it exists there, we're going to have our triacylglycerides, and that just builds up our adipose tissue as a storage, because those can then be broken back down into glucose if needed for energy. And then our muscle also converts excess glucose from its systems into glycogen in its stores. During elevated activity, we're going to do the exact opposite. We're going to use all the glucose we have, and then when we need more, we're going to start breaking down our glycogen reserves. And this can be because our whole body is working as we're running or we're climbing, or it could be in a very reserved spot. For example, if you're writing with your right hand to take notes, those muscles are using more energy than your your resting hand. So it's going to be doing different processes than the muscles in your left hand. If no glucose is available, that glycogen will be broke down, and then we're actually going to keep using what's left over that hasn't been used, such as lactate. It's going to be pushed into the liver through the bloodstream, converted back into pyruvate, and then kicked back into the muscles so it can be used again as energy in the citric acid cycle. And that's pretty cool because our body will just reuse its excess products from the reactions it creates. And then, if we're hungry, if we're really low on energy, then we can burn into our fat reserves, which a lot of people try to do so they can lose weight. But those triacylglycerols from adipose tissue can be converted into fatty acids, sent into muscle, converted into acetyl-CoA, and then again put into that citric acid cycle so that we can have more energy, even if we haven't eaten enough glucose to provide what we're doing, or if we're doing a lot of exercise. And then as a last resort, protein will also be broken down from our muscles. The amines from those amino acids will be put into the urea cycle, and the rest of it can be metabolized into further energy. And I do want to mention that insulin really is key to all of this because it turns on or off our different processes to make glycogen or to break it down if it's gone. And then diabetes is a big issue with that because we need our energy, but if we're not reacting to the insulin, it's not going to work properly. Thank you.